and we use the product to sum formulas, and I will provide you these things in their entirety. Okay, there's 4 of them that are very similar, but I do expect you to know, because it's the only way you can really address the problem. Know to recognize that that format there matches that format there, correct? And that's what we're doing a lot of in these questions where we're trying to simplify something, is that we recognize formats. We recognize similarities between what we have and some identities and other formulas that we've already created. So we're going to simplify this so that there exists no multiple angles. And what I mean by that is that 3x is referred to as a multiple angle because it's got a multiplier out in front, right? It's got that 3 out there. So I want to leave everything so that it has a 1x essentially as the argument, okay? And we can do this no matter what those values are, okay? And I kind of showed you on the whiteboard up there, still up there, dealing yesterday with like an 8x and a 2x, okay? But the larger those coefficients are for x, the more multiplications that you have to do, the more substitutions that we end up having here in a minute or a moment. So doing it with 3x, I think, is going to kind of open your eyes to what happens, but we could do it with 4x, 5x, 6x. It's just a kind of a repetitive process if we're using larger values. All right, so we're just going to simply take this and rewrite it in that format. Okay, so sine of 3x cosine x turns into 1/2. Now sine, so u and v are your 3x and your x. So 3x is u, x is v. So when I add those, I'm going to get 4x. Plus then when I subtract them, I get 2x. Be cautious of that when you're doing the subtraction. If v was bigger than u, you would have a negative argument, right? And when you have a negative argument, say you would end up with sine of negative 2x, you would want to use one of your cofunction identities and rewrite it as negative sine of 2x. Does that make sense? So there could be a substitution in there, just depending on the size of x and 3x in relation to one another, size of u and v, that might incorporate a second substitution here that we don't necessarily see in this example. I'm going to go ahead and distribute the 1/2. Let's get 1/2 sine of 4x plus 1/2 sine of 2x. Okay. I just like, if I've got something to distribute, I like doing that. It's not necessary at that stage if you don't want to. If you want to make your substitutions, leave that 1/2 out in front, you can. I make more mistakes if I don't do that right away. Okay. But if I look at this, what's nice now is that expression right there, sine of 2x. Sine of 2x, hopefully you know, sine of 2x is a double angle, right? And that turns into 2 sine x cosine x. All right, so that's, having my reference sheets next to me or something like that, that might be nice to have so that when I see sine of 2x, I can replace it, okay? So I'm going to write this below it, 1/2 2 sine x cosine x. What's going to happen with the 1/2? Or the 1/2 and the 2? Yeah, they multiply together to give me 1, so we just get sine x cosine x. Now, what's nice about that is, what are those arguments? Are they multiple angles anymore? No, okay? So we have taken that thing and rewritten it as sine x cosine x, okay? Now what comes as kind of the hard part of this question is doing the same thing with that expression there, 1/2 sine of 4x. Because 4x is not a double angle directly, okay? But it is a number times 2, isn't it? Or a quantity times 2. So we can do a little bit of work here to express it as a double angle, okay? And this is something that you would do if this was any even number greater than 2. So you would do this if it's 4, you would do if it's 6, 8, whatever, okay? You're going to say let 2u equal that argument, okay? Let 2u equal 4x. And then you're going to say, then u, what would u equal? U would equal 2x then, right? Just divide both sides of this little thing here by 2, and you get u equals 2x, right? Now make that substitution. Take this 4x and rewrite it as 2u. Does that make sense? Is that now a double angle? Yeah, but it's in terms of u, right? So we're always going to remind ourselves of that. But this means now 1/2 sine of 2u. It's this thing over here again, but now just reminding that my variable I'm using is u. So it's going to become 1/2 2 sine of u cosine of u. What's going to happen with the 1/2 and the 2 again? Cancel. So I'm left with sine of u cosine of u. So that's nice. Those little arrows that I'm writing there, you read them as like implies, okay? So this implies that, this implies that, that implies. So sine u, what was u? It was 2x. So now let's make that back substitution. And what's nice is that that expression right there is the same thing as 1/2 sine of 4x. Is that okay? But what was nice about it? The 4x no longer exists. It's all 2x's now, right? Do we know that that expression right there turns into 2 sine x cosine x? And cosine of 2x, you've got options here for this one. I'll just come over to the side again. Remember cosine of 2x. That was either cosine squared x minus sine squared x. You could write it as 1 minus 2 sine squared x. Or you can write it as 2 cosine squared x minus 1. Any one of those three is fine for this substitution because they all have a 1x in them, right? Okay. Just to stay consistent with what we did in the last class, I used that one in the last class, so I'll use that substitution here. So this thing here is going to turn into 1 minus 2 sine squared x. All right, now, this is a singular term times a binomial, right? Let's distribute that through. 2 sine x cosine x when I multiply times the 1. And then when I multiply this times the 2 sine squared x, it becomes minus 4 sine squared x times sine x is sine cubed x, right? Times in the cosine x. So that's just taking that thing there and multiplying it by that. Okay? What is nice is that that thing right there, that line, is exactly the same as 1/2 sine of 4x. Okay. Now, the payoff is we got rid of the 4x, right? But doesn't the expression get a lot more kind of complex in regards to the ratios that we're using? But we got rid of the 4x. Now, remember we had this blue portion that we did that was, and we did that first because I thought that was maybe easier. That needs to be added down here. So I'll add plus sine x cosine x. Not what I wanted to do. Are these two terms like terms? Okay, so my final result here, just going to write it right here, becomes 3 sine x cosine x minus 4 sine cubed x cosine x. I apologize for the work that's everywhere. Hopefully on your paper you're not following the same kind of course time. Maybe you're going more of the linear, straight down when you're doing the work. But that should be the same thing as sine 3x cosine x. Okay. Obviously, what we have there in that blue box is a lot more complex looking than sine 3x cosine x. However, like I said, the cost of or the cost and payoff, or whatever you want to refer it to, refer as, or refer to it as, is that we've gotten rid of the multiple angles. Okay, so that was the goal. Okay, but the cost of that is then the expression is a lot more complex looking, right? Okay. How can I gauge whether we've done this correctly? Go to one of your graphing tools. Okay, type in sine of 3x times cosine of x, and you get that orange curve. Then I should get the same thing with, what was it, 3? Was it 3 sine x cosine x? Yeah. And then minus 4 sine cubed. Desmos doesn't know what sine cubed looks like when I type it in with an exponent right here where my cursor is. So I have to do it this way. And then it was cosine x. And we see that the orange and purple curves are identical, right? Okay. If we wanted to, we could maybe factor a sine x cosine x out. So I have sine x cosine x. And that would leave me 3 minus 4 sine squared. It does know what to do with sine squared. X like that. Okay. So the black and the orange are the same, right? And the benefit of this might be eventually a goal we might have is to be able to solve this thing for x. So this thing would look, maybe I could do this. Now this isn't necessarily a difference of perfect squares, but we can write it as one. We can do this. All right, that's cosine of x. Okay, let's see, and then we go the square root of 3 minus 2 sine of x. So make sure I get the right parentheses, and then we go square root of 3 plus sine of x. I've got something messed up somewhere. Oh, I forgot the 2's. So 2, 2. There we go. Okay. So whenever even though that's not a perfect square, right? That 3 is not perfect square. You can, because we know how squares and radicals work, we can write it as radical 3. And then we write that 3 minus 4 times squared x as the product of its conjugates. And that might be a beneficial thing to do when solving for this thing. When maybe we're asked, when is this thing equal to 0? When does it cross the x-axis? That might be a process that we want to go through. Okay? Does that kind of make sense to everyone? Right now, don't worry too much about going that far when we need to do that with our equations. We can do that later on. But the question yesterday was, do we stop? Do we stop right here once we make this first substitution right there? Do we stop there? Well, it depends on how the question is phrased. Okay, if it just says make the substitution and simplify, and they don't say how far, then I would say they're probably asking you to stop there. Okay, or they might say write the product to a sum. Well, that is taking the product of sine 3x cosine x to the sum of 1/2 sine 4x plus 1/2 sine 2x. So you could stop there. But if they write the directions this way, okay, or in some version of that, then you need to go further, and that's the process of going further. And if, for instance, this was an 8x, this 4 here, if that was an 8x, or I don't know what's going on. There we go. Let's say this argument here, after we applied the sum, was an 8x. We would do the exact same thing. We would just let this be, we let 2u equal, my cursor keeps lagging really bad. All right, we let that be 8x. This would then become 4x, and now you would see this is 2u. We would still make that substitution that 2u is equal to 8x, so that becomes 2u. But now when we make these substitutions down here, u is 4x, right? So that would be 4x there, 4x there. And now we would have to do another u substitution and say, okay, now probably using a different variable, we'll probably say w, let w, or 2w equal 4x. So then w is equal to 2x, and make that u substitution again, and you keep doing that iterative process until you dwindle everything down to 1x. Does that make sense? Okay. So the one on the whiteboard up there on the left-hand side, where it says sine of 8x, that's kind of where we would kind of go through that process and use multiple u substitution processes. There's also the question, well, what happens what if we get into this thing, we get 1/2, now it becomes sine of maybe 5x plus then sine of 2x. Well, how do I address that? Because sine of 5x, okay, we don't want to usually, if I write u equal, or 2u equals 5x, then u is going to equal 5/2 x, right? That's kind of ugly. Maybe we don't want to deal with that. Can we write sine of 5x as this? Is that still 5x? And that's a sum and difference, isn't it? Or addition formula. So I can write this as sine of 4x, cosine of 1x, plus then cosine of 4x, sine of 1x. Then you would have all that stuff down here as well. Okay, and then you can start addressing, okay, how do I change that 4x? How do I change that 4x? And so forth. And keep going from there. Does that make sense, everyone? Okay. So no matter whether the arguments are even or odd or greater than 1, we should always be able to break them down so that they are kind of manageable, okay? Through substitutions, we can get them all the way down to 1x when necessary, okay? And that might be beneficial to us in regards to eventually solving some equations. We'll see how elaborate some of the equations we get into are going to be, and then whether we need those or not. So that being said, let's go through. I think it's a good idea to do a couple more examples that are similar to what we've seen maybe on the quiz. I know we struggle with some of those, so we do have a little bit of time today. We can go through some more examples that are similar to those. Now, I can't remember, did we go over this one in class yesterday? We didn't get to that one? Okay. All of this is, guys, is it's using, if we see sine 3x minus sine x, okay, sine of u essentially, or sine of x, minus sine of y, or sine of e, however, whatever variables you want to use. So this is in this format here, sine of something, I'll just use u here, minus sine of something different, so I use v. Come back up here. Do we have a formula like that, sine of something minus sine of something different? Okay, so I'm going to use that formula right there. Okay, so I'm going to rewrite this numerator here. My left-hand side. I'm just going to scroll down so I have a little bit more room. Oops. All right, so we're going to rewrite this numerator here as 2. So this is the left-hand side. Becomes 2, and then we had cosine. Now it's, the argument is that plus that divided by 2. They're calling, if we go up to our formulas, it's 2 cosine of x plus y over 2 sine of x minus y over 2. Where x and y's, they're calling that x, and they're calling that y, or u and v. I don't necessarily like using x and y here because of that x showing up in the problem, but it doesn't matter. So we're going to add those together, so you get 4x over 2, which just becomes 2x, right? Does that make sense? If I subtract them, I get 3x minus x is 2x. 2x divided by 2 is just x. So we get sine of x. Okay? The bottom, okay, the cosine 3x plus cosine x. If we look up here, scroll again, it's this one here, cosine of something plus cosine of something different is equal to 2 cosine of x plus y over 2 cosine of x minus y over 2. So we're using that identity in the bottom here. Okay, so it becomes 2 cosine of them added together divided by 2. So 3x plus x gives me 4x divided by 2 gives me 2x. And now cosine of them subtracted, so 3x minus x gives me 2x. And then divide by 2 just gives me x again, right? What's nice about that stuff right there? Cancel out. Gives me 1. What's sine x divided by cosine x? Tangent x, which is your right-hand side. Okay. If you were to graph that thing, okay, remember what tangent looks like? That's pi over 2, negative pi over 2. That's pi over 2. Tangent's going to kind of look like that, right? So if I graph this left-hand side in one of our calculators, that's the image that I'm going to get. And it's going to repeat itself over and over again. Okay? Is that doable? All right, so that's addressing the product and sum and some of the products. This is the substitutions there we were using. These are sums, so we're changing them to products. These here are two examples that I don't think usually are maybe student friendly. Usually people don't like them. Um, but I think we should be able to navigate these pretty easily after seeing a couple examples. And when we've done maybe two of these already, it says sine of 1/2 cosine inverse of x. Remember that this here is a way of them providing you an angle, isn't it? Okay, so that is going to be an angle, and I'm just going to say theta is my angle. Okay, so that thing is going to eventually give me some theta. Now we're going to have to do some work because I can't just make that substitution. There's something that's going on here that's going to kind of develop in a picture. But if I do that, then I've got the 1/2 that's still there, and now I've got my sine out in front, right? So do we see it? This is a half angle formula question. Okay, because normally it's sine of theta, but now we got sine of half of theta. Okay, so how do we address that? Well, I need to know what this theta is. In order to kind of evaluate this so I have an algebraic expression only in x, I need to draw a picture. Okay, remember what that x is, because this is for the x as being an input of your arc cosine, right? Okay, and it's spitting out an angle. If it's spitting out an angle, the input would have been a what? A ratio. Okay, and because it's cosine, that ratio is an adjacent side divided by hypotenuse, isn't it? So let's draw a picture of this, and I'm going to say, whenever we do is, if you just want to draw the triangle, that's fine. I like to draw the triangle in the first quadrant. But if I do this, so the angle theta that I'm going to get is actually that theta right there. Does that kind of make sense? Okay. And if cosine inverse is x, cosine inverse is x, as a fraction, that's x over 1, right? So the adjacent side is x, and the hypotenuse is 1. Can we use the Pythagorean theorem to find this distance over here? It's going to become 1 minus x squared underneath the square root, isn't it? If I maybe I call that my side y, I would have x squared plus y squared is equal to 1, and now I want to solve for that y. Okay, and that's what I would get there. So now we should be able to kind of evaluate this out, because we know that the sine of 1/2 theta is plus or minus, okay, 1 minus cosine theta over 2. That's the formula that we are provided with for the half angle for sine. Why is the picture necessary? Is because this formula incorporates a full theta, right? And if I look at this full theta, can I say then that 1 minus cosine theta, 1 minus cosine theta, isn't cosine theta? What is cosine of theta in this problem? It's x, right? X over 1. And then I divide by 2. So sine of 1/2 cosine inverse of x should look like that. Okay. Now I'm going to kind of talk about some things here in a little bit when we check this and graph this to see what's going on. Right now, our information was in the first quadrant, right? Okay. And therefore, if our information is in the first quadrant, shouldn't sine in the first quadrant be positive? Okay, so I'm going to Sine should be positive, so then half a sine should also be positive, or not half a sine, but half of the sine of half of theta should be positive as well. So that's why I can just look at the positive version of this. So I'm going to go to Desmos, and I'm going to see what this thing looks like. Actually, no, I'm not. I'm going to go to GeoGebra and do it. All right, so if I have sine of 1/2 cosine inverse of x, it looks like that curve right there. Okay? And this is the reason I'm doing this in GeoGebra, because I can get this side-by-side view here. I'm now going to type in what we just came up with. We came up with it equating algebraically as a square root. Was it 1 minus x all over 2? So it became that. Okay? They are different, aren't they? Okay, but now if you think about it, the only reason that they're different is because this one extends on forever in the negative direction, right? This one is stuck here, ending at -1. Why? Remember when we took cosine, the curve cosine, and we essentially took that little portion right there, and that was the portion between 0 and pi. That was the portion that we flipped on the line y equals x to find the inverse, right? Okay. So right now, the domain of that thing goes from 0 to pi. So the domain of cosine right now that we're going to look at goes from 0 to pi. And what would the range go to then? What is that smallest y value we get there? -1. What's the largest y value? 1. Okay? So then when we take the cosine inverse, okay, doesn't this range here become the domain for the inverse? And the range is now the domain of this, so it becomes 0 to pi. Now, why do I have to talk about that? Why are we interested in that? That is the reason why this maroon curve over here is not moving to the left like this green one is. Okay? Because if I'm going to evaluate the sine, and the sine inside its argument is incorporating the arc cosine or cosine inverse, the only things that I can type in to that cosine inverse are numbers that are between -1 and 1. Because if I do this, let's put in, I just ask to evaluate arc cosine of -2. It says undefined, right? So if I take sine of 1/2 of an undefined value, what's 1/2 of an undefined value? Undefined value, right? Can I take the sine of an undefined value? No. Okay? So this innermost function here is dictating what I can do with this outer function, because I can only use this outer function on defined values, right? So from -1 to 1, or outside that range, or that domain of -1 to 1, this here becomes an undefined value. Okay? So to get these two things to equate, I have to use the same inputs in this one that I used in this one. So the only inputs I could use here are between -1 and 1, right? So on this one, I'm going to restrict it to -1 and 1. And now you see that those two things do indeed look the same then, right? Okay. That is something that's kind of overlooked a lot in these questions. And even WebAssign might not address it. They might not ask you to provide the restriction on the domain so that the algebraic expression is identical to the trigonometric expression, but it is a necessity, okay? And a lot of geometry classes kind of overlooked it. I think that's very important to think about. Um, the same thing happens, guys, down here in the bottom in example 7, I think it is. You're going to draw a picture, so this is going to give us a theta. This is a ratio of what now? Is it adjacent over hypotenuse anymore? It's opposite over hypotenuse, okay? And now what's going to happen when we do that, this 2 is still out there, right? And now we're getting cosine of a double angle instead of sine of a half angle, right? Okay? But you still need to draw your picture. So I get my triangle here. Okay? This is x over 1, so opposite of x, or opposite is x. Hypotenuse is 1. The Pythagorean theorem is going to tell you that that's 1 minus x squared, giving us that angle being theta. Okay? So cosine of 2 theta. We know there's 3 versions of that. I'm just going to write it as this. Which is the same thing as this. And I like to write it that way because what is sine of theta over here? X. So we get 1 minus 2. This becomes x, and we'll square that x. That is the same thing then as cosine of 2 sine inverse of x. But think about this. What are the only values that you can plug in for sine inverse of x? Giving you the picture here of sine inverse real quick. What are the only domain values for sine inverse? -1 to 1, right? Okay. So when I'm asked the cosine of 2 arc sine of x, and I'm trying to get that curve, okay, notice how its domain is -1 to 1, right? That's because that little expression right there is forcing that, okay? That this is a composition of functions, right? Okay, so that innermost domain is going to play a role. Now, if I type in 1, so I'll do it over here in this one, type in 1 minus 2x squared, we see that those two things are very similar, right? Okay, and you did even see that when I was typing it in, if I put it in that second graphic, the blue one and the orange one do overlap, right? But how do I restrict the orange one so that it is exactly the same as the blue one? I use that same domain. -1 is less than x is less than 1. And there we've got our algebraic expression in regards to x. Now, what's the nice part of having that? We probably feel a little bit more comfortable with our algebra than what we do with our trigonometry. So if I was asked to kind of evaluate this thing at multiple values of x, so like x being 0, pi over 3, pi over 6, pi over 12, or something like that, in this, I have to address my unit circle multiple times, right? Down here, I don't have to do that. I just have to square pi over 3, pi over 6, that kind of stuff, and evaluate that way. Does that make sense? So this might be logistically a better equation to mess around with when trying to evaluate it at multiple spots. Okay. Obviously, we're out of time here to do some more examples here. Tomorrow, I think what we'll do is start off with maybe example 8 and 9. But I find it very important that we do examples 10 and 11. Regardless of what we start with tomorrow, we will do those two. And those are the last examples out of this section that I want to mess around with. I have posted a second 7.3 assignment right now, looking at it being due Thursday, to force you to start working with more of this stuff. Okay? I've been kind of lax on the amount of homework I've been giving you guys, at least I think, in my opinion. To really, really get good at this. The more exposure to it, the more times you see it, because they're very repetitive types of problems, right? I think you're getting much better at learning those formulas. Tomorrow, at some point, I want to get into 7.4 and start talking about how to solve some of these equations, which the equation portion is the reason for learning 7.1, 7.2, and 7.3. Okay? Because those things, those formats are going to pop up inside equations. We want to make those substitutions to make those equations a little bit easier for us to solve. Okay? What you find out with the equations, solving trigonometric equations, is it's kind of now a merging of college algebra and trigonometry. Okay? So we're going to have to bring our factoring, maybe use a quadratic formula, sometimes the rational root there and that kind of stuff. Solve.
Have a good day.
Okay.